Hello, my name is Trevor Ford, and today I will be introducing you to general chemistry. At the time of the making of this video, I had just graduated high school and completed an online AP chemistry course. I plan to continue my education with the pursuit of a bachelor's degree in chemistry and a bachelor's degree in physics, and eventually hope to go to a graduate school program. But for the time being, I wish to share my own knowledge and solidify it within my mind. Over this summer, I wish to further my own understanding of the topics I learned by making this YouTube series to explain the topics to others as best I possibly can. It is said that teaching is the best way to learn. In this series, you can expect all general chemistry topics from a basic introduction to the science of chemistry itself to the crystal field theory of metal complexes. Before every lecture, I'll give a table of contents like this one here so you can prepare sections for your notes and see what we'll cover. As you can see, we have a lot of material to cover today, so let's get started. So I'll start by asking, what exactly is chemistry? Chemistry is the study of the composition, properties, and interactions of matter. Chemistry also encompasses how energy and matter interact and are interrelated. You may be skeptical as to how any of this will be of any benefit to you in the future, but the concepts introduced in chemistry actually have applications to many other fields and to interesting phenomena that are scattered around our world. For example, take the blood in your body. Normally a biology topic, right? You should know from basic biology that hemoglobin contains iron. But what exactly does that tell you? Well, the way I explain it doesn't tell you much. Using chemistry, however, we can actually verify the structure of the hemoglobin, which, by the way, is a metal complex. When we can verify the structure, we can actually begin to see how its structure relates to its function and how certain disorders, such as anemia, alter the shape of the complex and why these disorders can be so detrimental. Throughout this series, I'll try to give as many real-world examples as I possibly can think of, since I know many people would enjoy applying their knowledge rather than just discussing theories. Now that we have discussed what chemistry is and why you should try to understand it, it is time to get started with the learning. I'd like to continue today with a discussion on significant figures. Yes, those pesky rules that may bother you in other areas such as mathematics or physics will again bother you here in chemistry, but I promise that they aren't nearly as tricky as they're made out to be. Here I have some decimals, and we're going to determine the number of significant digits in each of them. Pretty simple task, I hope. So we'll start with this 0100.040. We should all know that the first zero is a placeholder, and such a placeholder doesn't actually contribute any value to a number. Now, any non-zero number will always be a significant figure. That is very important to know. There are two non-zero numbers in this problem, so we know there should be at least two significant figures. Significant zeros, however, are by far the hardest to determine and understand why they are significant. Luckily, there are some simple rules we can follow. All zeros between two significant figures are significant themselves. So in our first example, the zeros between 1 and 4 are significant. Trailing zeros, that is, those reported zeros at the end of numbers that don't appear to be adding any value to numbers, are also significant. This would be the zero right after our 4 in our example. They may seem useless, but they actually are very important because they give a clue to the precision of the number that is being worked with. However, we run into a problem when we start to define these. What happens to zeros after significant figures before decimals, or in numbers without decimals at all? When I'm talking about the significant zeros here, I mean the trailing zeros that come after the last significant digit that you see that is not a zero. The answer to this is actually a little tricky. It all depends. If there's a decimal place at the end of all the zeros, they're significant. If not, they're just not. We'll do a bit more practice later. Now, there's another rule for significant zeros that is actually pretty important, but is also very, what's the word I'm looking for? It's also very obvious. Zeros that come to the left of all significant figures, like I said earlier with placeholder, those zeros are all insignificant because they don't actually contribute anything to the number. So why must they burden us with all these rules, right? Well, these rules are actually a safeguard to ensure our results aren't more precise than our measurements. If the theoretical values are based on experimental values and recorded as if the experimental values were exact, there would be many incorrect assumptions to be made about the world we live in. That's a lot to take in. We'll take a quick break and look through the examples here to determine the number of significant figures in just a moment. So hopefully you enjoyed your break. I know it wasn't very long. You could have paused if you needed to. Now, the next two numbers here are going to be a little more tricky than our first number, even though they may not look it. We're actually going to apply the trailing zeros rule with decimals and without decimals. So our first number is 100, and the second number is 100 with a decimal point. What's the difference, right? They all have the same value. Well, the point is, with the 100 without the decimal, we don't know if that's been rounded to the hundreds place, to the tens place, to the ones place, if at all. So that's why the 100 that doesn't have the decimal is much less precise than the 100 with the decimal. That's also why we only count the first number in the 100, because it's the only thing that we can be certain that is adding actual value to the experimental result that was given. For the other one, we have the decimal after it, so all of the zeros are going to be significant because we know that it had to be rounded to either the ones place or the tens place or something after that. So we at least know up to the ones place, and we start with the hundreds. So we go hundreds, tens, and ones to get 3 significant figures. So here come a bit more examples that we can do on our own. And I've listed the numbers out the side of them. So I want to see if you can work the problems themselves and then determine why the answer is what it is. So the first number we'll look at is 5,079.8090. I'll give you 5 seconds, so if you need more time, pause the video now. Alright, so the first step is to count the number of non-zero numbers. 1, 2, 3, 4, 5. Then add the numbers between significant figures, 6, 7. And then add your trailing zeros, 8. We know the trailing zero is significant in this case because it comes after a decimal point. Remember that if the number does not even have a decimal point in it, trailing zeros will never be counted. So overall, there are 8 figures in this number that are significant. So next we have 87,000 and 87,000 again, but the second one has a decimal point. 5 seconds. So you should see that 87,000 without the decimal has 2 significant figures, while the decimal point with the decimal point it has 5. Why is this? Because when we record 87,000 without the decimal, we don't know if the result was rounded to the nearest 1,000, 100, 10, or 1. But in this case, where we have the decimal, we are certain that it is rounded to at least the ones place. Okay, one more. 0008.80000. You have 5 seconds. Okay, you should have 6 as your answer. All good? If not, please feel free to comment below and ask for more assistance. You can also send me an email and I will try to respond to those as quickly as possible. My email will be in the description or at the end of this video, whichever you wish to see first. Now we're going to talk about how you should report your answers to problems. That is, how many significant digits you should use. You never want an answer to be more precise than a measurement that is given, because all measurements involve at least a small degree of uncertainty. For this reason, you should record your final answer with the same number of significant figures as the measurement given with the least amount of significant figures. This applies to all mathematical operations in which values are not perfectly precise. To record properly, simply perform the operation, then round the answer to the proper number of digits. Be sure to include trailing zeros if necessary. One important note about the calculations, you do not want to round to the proper number of significant digits in any intermediate calculation, only round your final answer. We're going to get a little more practice with this, so feel free to pause now and grab a calculator if you think you may need one. So our first example is 9.2 plus 3.67. Take some time to work the problem out on your own, and pause the video if necessary. We'll work through it when you're ready. Okay, so you should have remembered that the first step in this would be to add the numbers, either in your head, on paper, or in a calculator. When you add them, you should get 12.87. Now we're going to trim this result down to the proper number of significant digits. We can count using the rules mentioned earlier that 9.2 has 2 significant figures, while 3.67 has 3. We see that all given numbers in the answer are significant, so we are currently at 4. Round everything but 2 digits out of there. You round to get 2 significant figures because 2 digits is the least precise measurement. So 12.87 with 4 significant figures rounds to 13 with 2 significant figures. You can include a decimal if you want, but in this case it does not matter because the amount of significant digits will not change. Okay, so here we have sine of 3.48 degrees. This is a trigonometric function, so I am assuming that you do know a little bit of trigonometry, or at least know how to put it in your calculator. So remember that all mathematical operations are included in the definition of operations on significant figures. This includes trig functions and log functions. So we'll simply plug this into the calculator and round as necessary. I will give you some time to do that. So you'll see that the result is a long decimal, but we only want 3 figures because that's our least precise measurement. So all we do is round accordingly. Our answer will be 0.0607. Remember that 0 is to the left of our first significant figure that's non-zero. Those are all insignificant. One more. So we have a subtraction with 3 numbers, 10 with a decimal point, minus 2.3, minus 0.37. Take the time to work through this, pause if necessary. Okay, so you should notice that all 3 measurements have 2 significant digits, so that's how many our answer should have. Plug it in the handy calculator and you find that the overall result will be 7.33. Round to the nearest 2 significant figures, which gives a final answer of 7.3. In a case like this, where you can have intermediate steps, you only want to round your final answer because it will be closer to the expected value than the one that has been previously rounded and then used again in the calculation. Never round intermediate steps. Got it? Good. If not, feel free to comment below for more help, or if you have any questions, or you can send me an email. So the next important thing to note is exact numbers. What exactly is an exact number? How can anything be exact according to the rules of significant figures? Well, it turns out that definitions for subjects, like conversions or for integers in certain atomic models, are actually exact numbers. Examples of exact numbers include 12 inches per 1 foot and 1,000 meters per 1 kilometer. Any kind of conversion factor is an exact number because these conversions in units are defined by humans and are not determined by the universe. The most important thing to note about exact numbers is that they do not get counted in significant figure calculations to determine answer precision. This is because they don't have any uncertainty. So say I have 3.475 feet and I want that in inches. I'd multiply by 12 and round the answer to 4 significant figures because 12 is an exact number. It doesn't get counted. You can think of it as being 12.000 with infinitely many zeros. So it's time to move on to the next discussion for this lecture, precision and accuracy. The first note we should make is that it's possible to be accurate but not precise, and it is also possible to be precise but not accurate. Accuracy refers to the closeness of measurements in a series to the expected result, whereas precision refers to the closeness of measurements in a series to one another. Think of precision as shooting a target and hitting all bullets or arrows around the same area, and think of accuracy like shooting at the same target and getting a bullseye with one arrow, and then being all over the place with the other arrows. So we're going to take a quick oral quiz now, just one question, I promise it's not hard. If the expected value of an experiment is 8, and I get values of 3, 2, and 4 on 3 trials, am I accurate and precise? Precise but not accurate? Accurate but not precise? Or neither precise nor accurate? I'll give you 5 seconds to think about that. Pause if you need more time. So in this example, I'd be precise but not accurate. All of my results were around the same general area, but none of them were close to the actual answer. Okay, so we've covered significant figures and distinguished between accuracy and precision. If you have any more questions, leave them in the comments below, or as always, you can still send me an email. So we still have a few more things to cover today. I know it's starting to get a little long, but hang in there. Chemistry is really fun once you get the hang of it. So I'd like to continue our discussion further by now talking about extensive and intensive properties. Please note that these are not chemical and physical properties. So what do I mean by extensive and intensive properties? The best way I'd like to explain it is that extensive properties depend on the extent of the amount of the material you have, while intensive properties are properties that remain constant regardless of the amount you have in the sample. A good way to remember intensive properties is to remember that some short people are very intense, so size doesn't matter in your intensity. It's a little silly to think about, but that's how I would remember it. Examples of your extensive properties would include your mass and your volume, while examples of your intensive properties would include your viscosity and temperature. Basically, anything that doesn't depend on the amount of what you have is intensive, whereas if you have a lot of it and it changes the value of something, that would be an extensive property. So another quick comprehension check like last time. Is color an intensive or extensive property? As always, pause if you need more time. So I'd like to break this problem up into 2 sections for you. The color of a solid will not change no matter how much solid you pile up, because like adding some solid to a pile won't cause the color to change. So color is definitely an intensive property there. Now, aqueous solutions may be a bit confusing because they're made of solutions with water, and that dilutes the color, but it only causes a change in color. Dilution does, because as more water is added, you'll see that it starts to get fainter, but the wavelength of the light produced by the solution will not change. It's important to note, again, that extensive and intensive properties are not physical and chemical properties. If you're interested in a discussion on the latter, I'd recommend simply looking up examples. All properties will follow a general trend that allow them to be categorized appropriately, and I don't really feel like they're that important because most physical properties would depend on stuff like chemical properties. Like, for example, magnetism is a physical property according to the definition. You would say, oh, okay, it's physical, but magnetism is actually determined by the electron configuration of the atom or element or any other thing under observation. We're finally in the home stretch. So we have covered everything up until the point of two very important laws that guide the fundamental understanding of chemistry. I'm going to start with the law of conservation of mass. The law of conservation of mass says that in a chemical reaction or physical process, mass is neither created nor destroyed. It is conserved. Basically, you can't create more stuff where you don't have any. Chemical reactions just rearrange what mass you do have into new compounds, or breaks it apart into new elements or other compounds. Essentially, just know that mass cannot be created nor destroyed. And so lastly, we're going to talk about the law of conservation of energy, which says that in a chemical reaction or physical process, energy is neither created nor destroyed. It is converted into alternate forms, which is to say that it is conserved. Later in the course, we'll see how these properties are related, but for now, just take the time to understand that mass in the universe and energy in the universe are essentially constant. And know that chemical reactions, while they do release some energy, most of the times or absorb energy, it's absorbing energy from the universe, which still maintains that the overall energy and mass in the universe will stay constant. Okay, well, that's all I have for now. I hope you took some notes and that I may have been at least somewhat helpful in your endeavor to understand chemistry. If you have any questions about any content discussed here, please leave them in the comments section below. You can also email me at trevorfordchemistry@gmail.com. Thanks for watching, and I'll see you next time when we'll discuss the fundamental building block of all matter, the atom.